Hi, this is a quick introduction to linear regression. So basically, in order to understand what is linear regression, let's look at a very simple example and go through the example, and that will probably help us to understand why we need linear regression and some of the basics of linear regression. So let's assume that we are doing a survey in order to understand the savings of individuals in a particular city who are employed. So of course, let's assume that the city has a working population of about 1 million individuals. Now, of course, you cannot interview all 1 million individuals. So what we have done here is, normally you will interview a sample of, let's say, 5,000 or 10,000 individuals selected randomly. So let's assume that we have selected 20 individuals randomly, and we have asked them to give information about their annual salaries and their savings. So basically, the aim of this exercise in this case is to see what's the relationship between individuals' annual salary and their savings. Now, so we have got this information. You can see, for example, here the individual is earning quite high. It's 1.5 million per year, and the savings is $350,000. And again, here you can see someone earning 24,000 pounds $24,000 a year, but the savings is quite high. So of course, it doesn't mean that when your salary is going down, your savings are going down. Sometimes you have quite different views. Maybe this could be someone gave you an inheritance, or you would have got money from other means in addition to your salary. So the aim is to come up with a relationship between savings and annual salary, and that will help us to predict. For example, if we want to find out what would be the savings of someone earning, let's say, $2 million, or someone earning $50,000. So here we have $45,000, $39,000, but what could be the saving of someone earning $50,000? So, for example, those numbers are not here. But if we build a relationship between annual salary and savings based on the data we have, this is called sample data, because we have not taken the whole 1 million population's annual salary and savings, but we have only taken a part of the population. In this case, it's 20. Normally you would say, let's get information from 1,000 individuals or 5,000 individuals, etc. So that's what we call this a sample. So what we have done is we have plotted the samples in a diagram. So this is called the x-axis, and this is called the y-axis. Now in the x-axis we plot the variables that are called independent variables. In this case, it's annual salary. Now the reason we say it's independent is because annual salary is not based on your savings. Annual salary could be based on the kind of job you perform, the kind of demand and supply for that job in the present market or in the present economy, etc. And on the y-axis, so this is the y-axis, on the y-axis we have savings, which is called the dependent variable. Now the reason we call this dependent variable is, in this case, we are assuming your saving is dependent on your annual salary. So the y-axis is the dependent variable, in this case savings, and x-axis is your annual salary, which we call the independent variable. So, and we have plotted the points based on a survey. So remember, when we talk about linear regression, now what we are trying to say is, can we draw a straight line between these numbers? Of course, now we cannot join all the numbers, then it will not be a straight line. So the straight line we are going to draw will have to be an estimate. It's going to be an estimate. So when we talk about linear regression, basically what we are saying is, can we draw a linear or a straight line that will help us to predict the relationship between savings and annual salary? Because if you have a formula or a straight line, even if you want to know what would be the savings of someone who's earning $1 million, what would be the saving of someone who's earning $200,000, or even beyond 1.6 million, you can easily calculate them. So remember, when we talk about linear regression, what we are trying to say is, can we come up with a formula, linear relationship between the, in this case, annual salary and savings, that will help us to predict or estimate the savings of any individual with once we have a particular individual's annual salary. So that's the purpose of linear regression. Now in finance we use it quite a lot for various purposes. For example, let's assume that a company has just come public last year and the company's stock price has been steady, but if we want to know what could happen to the stock price if the market changes. So if we have another stock in the market which has been there for, let's say, for 10 years or 20 years, and we know that these two stocks are behaving quite closely, then we can use linear regression to predict stock prices beyond the 1 year horizon. So those are some of the uses of linear regression, and linear regression is also used heavily in various financial analysis. So the question becomes, how can I draw a line? Now, can I draw it like this, or can I draw it like this? Which is the best line to draw in order to, because you can see they are quite widely spread. You know, they are not all close to each other. They are widely spread. So how can I draw a linear line and establish a relationship in order to predict any individual savings based on their salary? So what we have done here, so here, so this is the linear regression. So this is the line. Now you can see already this line, the linear regression is only an estimate. Now that's very important to remember. So what we mean by that is, if someone says, I want to find the savings of an individual who's earning $1 million based on this linear regression. Now this is the formula of the linear regression. I'll explain that to you in a short while. So the savings that you will calculate based on the linear regression will be only an estimate. Now that's important to remember. So you can see, for example, here, based on the linear regression, if we take the salary of this individual, which is $800,000 or closer to $800,000, this individual here, we will say the savings should be somewhere here, which is around closer to $200,000. But you can see this individual savings is much high. So you can see when you use a linear regression, it's only an estimate, because this is the actual value. This is the actual value. But based on the linear regression, you will say the savings is somewhere here. So it's only an estimate. So now when you draw the linear regression, you can see the linear regression will have a formula in this pattern. So y basically is it's a dependent variable. So in this case it's savings. Y is the dependent variable. Y equals the intercept. So intercept is where the straight line meets the y-axis. So the intercept is somewhere here, plus the slope. So slope is the how the savings vary or the savings change when salary changes. So that's the slope multiplied by x. So in this case x is salary. So this is the formula you can see. So basically what we are saying here is savings equals x. Now x is your salary. So 0.17 is 17%. So your savings equals 17% of your salary. So that 0.17 is your slope. 17% of your salary plus $87,000. So you can see already in this case this is the intercept. This is the intercept. In other words, if this is the intercept, in other words, if your salary is 0, based on this formula we are saying you will still have a savings of $87,000. Now of course you know that doesn't make sense. Every individual, because if your salary is 0, that means you're not working. every individual in the city who's not working will not have a savings of $87,000. We know that. So you can see already in the linear regression, the intercept doesn't make much sense. Now there are, in this example, now there are some other examples the intercept might make some sense. So that's something to remember. The intercept might not always make economical sense. So the other thing to remember is the slope here. What we are saying is, if your salary increases, let's say by $10,000, your savings will increase by only 17%. That's what the linear regression is saying, because here your savings equals 0.1735 times your salary. In other words, it's about 17.35%. So if your salary decreases, your saving will decrease by 17%. Not the actual savings, but the estimated savings based on the linear regression line. Now, the final thing, you might be thinking, what's the best line to draw? Because you can draw it like this, you can draw it like this. The way to decide that, now in Excel it automatically creates the best line for you, which is called the least square regression line. Now you can see in these blue arrows, I'm showing you the difference between what the linear regression line is telling you as your savings and your actual savings. In this case, your actual savings is here, if your salary is somewhere here. But the linear regression line is saying your savings is this, somewhere here on the line. So the difference is B. Now in this case, the difference is not that big, it's A. In this case, the difference is quite large, C. The difference here is D. And you can see sometimes the differences are positive, sometimes the differences are negative. And here also you will have differences. I'm just showing you very few. So what we do is we square the differences. So that's what we call it here, sum of squared errors. We square the differences. The reason we square is some of the differences are positive and some of the differences are negative. So we square the differences, and the line that has the least squared errors, so the sum of squared errors, where which line has the least or the smallest value, is the ordinary least square regression line. That's the regression line that suits this data. So remember the line, so remember you can draw so many lines, but the regression line that the most suitable for this data is the regression line that minimizes the sum of squared errors. So that's something to remember. As we go on, we will discuss more about the other assumptions around the ordinary least square regression line. So this is the basics. So remember, regression line is used to predict or to estimate the relationship between dependent variable and the independent variable. And whether a least square regression line is good or bad depends on how the data is spread. Now here, the data is spread quite widely. So the regression line is not a good estimate. For example, if you see here, the difference is quite high. Using the regression line, I will say my savings is somewhere here, but actual savings is very far. So you can see this regression line is not a good estimate, and the reason is because your data is spread quite widely. Your data is spread quite widely. I mean, here, this observation is very far from the linear regression line. And we will discuss about R squared later, but I've just shown it to you here. Now, if your R squared is closer to 1, that means the linear regression line is quite a good prediction of your data. In this case, it's not even closer to 1. It's 0.09. That means, but basically what we are saying is, you're not explaining the savings well using your salary. The salary is not explaining the change in savings quite well, because your R squared is very low. I will discuss about R squared later, but R squared helps you to say whether the linear regression model is quite good or bad. In this case, it's not that good. I mean, we can already see that there are some data which is very far from the linear regression line. So if I use the linear regression line, what I would estimate might not be closer to the actual values. So I hope you understood the basics. You can ask any questions, put a comments, and if you like the video, you can like it and subscribe for more videos. I'll be making more videos on similar topics and other topics in FRM. Thank you.